All right, let's look at this truss example. What I want to do is go through the calculations we need to solve this truss. So if you look at it, we've got a couple of, or a pin and a roller. First thing we need to do is look at static determinacy. Static determinacy, the formula is 2j equals m plus r. Okay, so if we look at this, we need to look at the number of joints. So it's 2 times 1, 2, 3, 4, 5. We have 5 joints equals the number of members. We have, let me switch to a highlighter. 1, 2, 3, 4, 5, 6, 7. So we have 7 plus the number of reaction forces. So earlier when you took notes over this, you should have noted that a roller has 1 reaction force and a pin is going to have 2. And I know where these are, but I'm not sure which direction they go, if they're positive or negative, but I know there are 3. So we go over here and put a 3. And when we look at this truss is statically determinate. We can see that 2 times the number of joints is 10 and 7 plus 3 is 10. So both sides are equal. That means we can continue analyzing this truss and the math will work out. If it's not, if these two numbers are not equal, then you can't do the math on this. You need to change the design of the truss or how it's connected. The next thing we need to do is look at the moments. Keep in mind that this point is fixed, so everything is rotating around this point. So we have a moment that is counterclockwise. No, this is clockwise, so this moment right here is negative. And we also have a moment acting here that is positive. So let's go look and see what happens there. Another thing you need to know is how long are these? So if you look at the bridge design, you can see that each grid is 10 by 10. So this one is 40 feet, also 40 feet. This one is 50 feet. This one is 50 feet. This one is 30 feet. Okay. So what we know is that the sum of the moments is equal to 0. One other thing we need to do, we need to label these points. So I'm gonna label these A, B, C, D, and E. That's gonna help us understand what we're looking at. So what this means is if we add all the moments up, that the sum of the moments is equal to 0, which means 0 is equal to moment A, which is positive, and we know that moment C is negative based on the direction of rotation. A is rotating this direction and C is rotating this direction. And remember, go back and look at our notes about how we know which way is positive and which is negative. So if I rearrange this formula, I get that if I move the minus MC to the other side, I get MA is equal to MC. Okay. Pay attention to your signs. If you mess up your signs, it's not going to go well. All right, so that means that whatever our reaction force our reaction force here, RAX, times that distance, which is 50, is equal to the moment at point C. So that is the force is 250 times 70. All right. If you rearrange this to solve for RAX, you get this, and when you complete that calculation, you get that RAX is positive 350 pounds. Okay, so go back and label your free body diagram. I would suggest duplicate the truss so that you can get your free body diagram completed. So this is RAX here, and that's not how I want that to look. And this is 350, and it's positive. Okay, so that's the first one. The next thing we look at, since we know RAX, let's look at the sum of the forces in the x direction. So we know that the sum of the forces in the x direction, because this is not moving, has to be equal to 0. That means that we can rewrite this as 0 equals whatever the reaction force is here at point D. So reaction force dx plus the positive reaction force at AX is equal to 0. So if we rearrange this to isolate the reaction force dx, we get that R dx is equal to negative RAX. So that means that R dx is equal to negative 350 lbs. So that means R dx is going this way, R dx minus 3. So the last thing for us to do is identify the reaction force at point D, y. So we know that the sum of the forces in y is going to be equal to 0. So we can rewrite this formula as 0 equals the reaction force at point D in the y direction. And if we look at this reaction force, right, or this force here, it is negative because it's going down in the y direction. So minus FC in the y direction, or we could just call it FC. Either way, just label it so that you understand what you are doing, and that's the main thing. So if we rearrange this to solve for R dy, we move FCy onto the other side of the equation by adding it to both sides, which means that R dy is equal to a positive 250 pounds. So that means this reaction force is going up. So reaction dy, that is positive 250. So if we look at this one is actually very simple. We have a reaction force here. That's not what I want. I need a pointer of some sort. Alright, so let's use a highlighter. So right here we have a reaction force going down, or the force going down, and a reaction force going up. Over here we have a force pushing to the right, and here we have a force pushing to the left. So that is the end of calculating the reaction forces. Take really good notes about the process. Think about what we did. First, we identified the moments and found one of the reaction forces, usually the one at the roller. And then we looked at the forces in the x direction, and then we looked at the forces in the y direction. If you have a choice, choose the simpler forces before you do the more complex ones. The next part is identifying the force acting on each member, and there is a fair amount of trig involved in that. But this is the solution for this practice problem.